All right, in this chapter, we are going to look at chemical bonding. First, we need to figure out why do atoms form a bond to begin with? Why would they bond? So first, we start by defining what's a chemical bond. So when we say a chemical bond is when you have two separate atoms come together and behave as a single unit. That's what a chemical bond is. Um, why would atoms want to give up their identity, their freedom, and become part of something else? And it is exactly what drives everything in nature, and that would be the tendency to exist in a lower energy state. For example, carbon and hydrogen come together to form methane, CH4. In the process, 1652 kilojoule of energy are released per mole. And the way atoms do this, they do it in three basic types of bonds. Ionic, and this is when you have a positive and negative entities are attracted together through electrostatic interaction between the ions. We call that type of bond ionic. Then we have covalent, and covalent is the result of sharing of electrons. Then we have metallic bonding, and this is when you have metal atoms bonded together. And the way bonding works is as follows. So we're going to focus first on ionic, then we move on to covalent, and lastly, we'll discuss metal bonding. As we started saying that bonding happens in order to lower the energy state of particles. So if we think about it, you'll see that electron and nuclei are continuously moving, and in that motion, they're doing it so they can rearrange themselves in order to optimize net attractive forces among electron and the nuclei. And we're talking about several of them together, right? But when a metal and a non-metal come in close contact, then an ionic bond will form. So let's take a look, for example, at the formation of sodium chloride. If we take a piece of sodium metal and put it in a flask that contains chlorine gas, the reaction will occur instantaneously and very vigorously. Now, if we look at the energetics of the reaction, we'll see that the ionization energy for sodium is around 495 kilojoule per mole to remove one electron, and to add an electron to a chlorine atom will give us back around 349 kilojoules. But when we look at those numbers, we see that they actually don't add up. Then if they don't add up, there must be something else driving the reaction, not just simply removing and adding an electron. So we see that the reaction happened very vigorously, then there must be something else, and that something else is that upon the transfer of electron from the metal to the nonmetal, we end up with a formation of a charge. So we have a sodium ion and a chloride ion. The newly formed ion get attracted to each other. That attraction, that electrostatic interaction, is the stabilizing force. Okay? So as a result, you end up with a network of interaction between plus and minus. And this leads to the formation of what's known as a crystal lattice. Okay? This structure right here is known as a crystal lattice. That's how most ionic compounds form. Now they do pack differently, and that's beyond the scope of this class. When you go on and take a higher chemistry class, you can learn all about it. But we call that electrostatic interaction an ionic bond. Okay? And that's what stabilize these compounds and lead to the formation of this crystal lattice. So if we were to zoom in a little bit, we'll see that they arrange geometrically in a fashion that can maximize interaction between opposite charges and minimize repulsion between like charges. All right. That's for ionic bonding. Now what happened, but the majority of this chapter, we're going to focus on covalent bonding. So what happens when two nonmetals come close? It will be no transfer of electrons if two nonmetals come close, but rather sharing of electrons. So the way you would think about it is the rearrangement is going to occur between the atoms in order to minimize repulsion and maximize attraction. By doing so, we end up with electrons concentrated between the two nuclei, and that concentration of electrons between the two nuclei is known as a covalent bond. Those electrons are going to be shared. All right, so when those electrons are shared, they lead to the formation of a molecular compound. And the smallest unit is known as a molecule. So if we were to look at the formation of a hydrogen molecule, we can use that as an example. So basically, you have the electron clouds, as we learned in the last chapter, and that electron cloud is going to change from the probability of finding it all around. Let me show you here, all around. So if we have a hydrogen atom, you'll have this a spherical shape of the s orbital where the electron is, and when they come close together, you'll see that the density moves from outside to be concentrated between the two nuclei, and this happens through what's known as orbital overlap. So when we look at the actual energetic of this bond formation, you'll see that the existence of this orbital overlap and that leads to the formation of a hydrogen molecule is much lower in energy than the individual hydrogen atoms alone. That difference in energy between individual atoms of hydrogen and the two hydrogen atoms together is known as the bond energy. That bond energy is the energy that is required to break the bond. All right, so that difference right here is the bond energy. The distance between the two nuclei right here, that gives us the lowest energy possible, because if we were to push them closer, the nuclei will be very close, and the electron clouds and the nuclei, the positive energy push versus the attraction to the electron cloud cannot overcompensate, and that will be very unfavorable. So this, the lowest energy possible down here, is the most favorable, and when we measure the distance between the two nuclei, that is the bond length. And the way orbital overlap will occur, let's say for the hydrogen atom, you see s orbital, but the result is going to be the two electrons have opposite spins, whether it's ss in the hydrogen molecule formation or a hydrogen fluoride formation. When you have s with a p orbital, you still have these opposite spin, or in the formation of a fluorine molecule, you'll have pp orbital overlap, and you still get opposite spins. Now that sharing of electron, if it were to occur between two identical atoms, like for example in a nitrogen molecule, then we call that bond a pure covalent bond. Okay, it's called a pure covalent bond. But if it were to happen between two dissimilar atoms, and so the electron pair will end up being shared unequally, then we're going to call it a polar covalent bond if they're shared unequally. So as a result, when the electrons are not shared equally, you're going to end up with higher electron density around one atom and lower electron density around the other. So the gain of electron density around one is going to equal the loss of electron density around the other. So the one that has higher electron density around it will gain a partial negative charge, whereas the other part will gain a partial positive. Okay, so we'll have partial negative and partial positive. Not full charge because we don't have an actual transfer of electrons like we saw in ionic bond formation, but rather in this unequal sharing of electrons, we'll see partial positive and partial negative. As a result of this, we end up with what's known as a bond dipole. Okay, a bond dipole or a dipole moment. When you have two equal but opposite charges. We are not going to calculate a bond dipole in this class, so don't worry about how we calculate it. But what we're going to do, if we look at the electron electrostatic potential map for hydrogen fluoride, we'll see that where the red is, that's negative, blue is positive. We'll see that the hydrogen, around the hydrogen, we have a partial positive charge, and we're going to use the Greek letter delta to indicate partiality of charge. And around fluoride, we'll see a partial negative. So in this hydrogen fluoride molecule, the electrons are more toward the fluoride than they are the hydrogen. The question becomes, how can we tell which atom is going to have partial negative and which one will have partial positive? What we're going to use is a scale that was established based on a lot of experimental data and a new scale, and we're given we're going to define a new property of atoms. We're going to call that electronegativity. And this is defined as the ability to attract bonding electrons. So when we look at the electronegativity values, and you see the scale is going to go from 0 to 4 maximum. Fluorine has the highest electronegativity. So anytime you have two atoms that are bonding, we can look at the difference in electronegativity between the bonding atoms. And the greater the difference, the greater the polarity of the bond is going to be. The atom with the higher electronegativities will have a partial negative on it, and the atoms with the lower electronegativity will have partial positive on it. From the graph, you can tell there is a general trend that electronegativity will increase as we move left to right on the periodic table, and from the bottom to the top, electronegativity will increase. Okay, so that's what we have. That's how electronegativity changes. Now we're going to define some cutoff points for whether our bond is going to be considered covalent bond, pure covalent bond, nonpolar, or polar covalent bond. So we're going to choose 0.4. Anything with 0.4 or less in terms of electronegativity difference. This is electronegativity difference. I'm going to write it as delta E N. That electronegativity difference, if it's from 0 to 0.4, we're going to consider that to be non-polar covalent. Okay, so we're going to call it non-polar covalent. Anything greater than 0.4, we're going to consider it to be polar covalent bond. Now you're going to ask me, say, but what about ionic bonds? So it depends. Usually some textbook give you a cutoff 1.8, some textbook cutoff 1.9, but it really doesn't matter. Anytime you see a metal with non-metal, it's ionic. Non-metal is going to be covalent, so I wouldn't worry about an upper limit on polar covalent bond. We're going to come back to polarity of bond. So for example here, let's look at the following. Arrange the following bonds from most to least polar. So I can look at this and see how they're like carbon versus fluorine, oxygen versus fluorine, and nitrogen versus fluorine. Fluorine has an electronegativity of 4.0. Carbon, it's 2.5. Nitrogen, it's 3.0. And oxygen is 3.5. All right, so this is the least polar, followed by NF, followed by CF. So if I were to put them from least polar to most polar, will be OF less polar than NF less polar than CF. All right, you can do the other two. That's pretty much, I mean, determining whether a bond is polar or not is very simple. On an exam, you will be given the electronegativity values. All you have to do is look up the difference. If the difference is greater than 0.4, your bond is polar. If it's less than 0.4, then your bond, if it equals 0.4 or less, then your bond is non-polar. As simple as that. Okay, I'm not going to spend any more time on that. But what we're going to spend most of our time is by looking at models, okay? Bonding models. And models are a way to explain how nature operates on the microscopic level. Now, some of these models will help us understand how atoms attach to each other. They're going to also help us understand why some combination of atoms are stable where others are not. For example, why is water H2O not HO or H3O? All right. But with any model, we have to be very careful. We must understand the assumptions in that model so we don't misuse it. That's key. And I'll point out some of these assumptions as we go along. So we're going to use to describe bonding something known as the localized electron model, where the molecule is composed of atoms that are bound together, and then they share pairs of electrons using overlapping of atomic orbitals. All right? We're going to describe the valence electron arrangement, and we come up with what's known as the Lewis model. Then we are going to use the VSEPR model, or valence shell electron pair repulsion, to help us predict the geometry. So we're going to look at how the atoms are arranged, then we're going to use the Lewis structure to predict the geometry using the VSEPR model. So we have two models. So first, let's look at the Lewis model. The Lewis model is simply a very convenient representation of the valence electrons. Since valence electrons are the only ones that participate in bonding, we're not going to worry about core electrons. We're going to focus on valence electrons. For core electrons, we're going to use the symbol of the element. As you see right here, silicon, Si. We're going to use Si to represent the core electrons. Then we're going to use dots to represent the valence electrons. Since silicon has 4 valence electrons, we're going to put 4 dots on it. And in the Lewis structure, 8 electrons in the valence shell is called an octet, and we're going to come back to what that means in a bit. But if we were to look at the nitrogen group, group 5, if we were to represent all the elements in the nitrogen group, we see that the only difference here is the symbol of the element only, but all of them have 5 dots. That should give us a hint that they might actually react in a similar manner. They might form bonds in a very similar way. And when other elements from other groups will have different dots, so they have different number of valence electrons, so they're going to react differently. They're going to form different number of bonds based on those dots. And the driving force of all of this is for all the elements want to attain an electron configuration like the noble gases. So they need 8 dots in their valence shell. And that's the driving force, and that's what we're going to look for. All right? So we're talking about ionic bonding and covalent bonding. When a metal loses an electron, so if we look at lithium, it has 1 electron. Once it loses that electron, when we write its Lewis symbol, we write it simply as Li+. So we do that for all cations. The moment they lose their valence electrons, those valence electrons are gone. So if we're looking at aluminum, for example, aluminum will have 1, 2, 3 dots. But if we want to look at aluminum ion, it'll be Al3+. We don't use dots anymore. When it comes for anions, on the other hand, when they gain electrons, what we do, so if we look at fluorine, for example, it has 7 valence electrons, therefore 7 dots. The fluoride ion will have 8 dots, so we put them 2 per side. Then we're going to have to put it in a bracket and indicate the charge. All right? That's how we represent the symbols of ions using the Lewis model. Now that Lewis model is going to be very useful in predicting the way atoms form bonds and how they're connected. All right? So the basis of this Lewis model is going to be the most stable arrangement of electrons, and that would be the octet rule. In other words, we are looking for an electron configuration very similar to the noble gases. So bonding is going to occur in atoms, so in order for them to attain a stable electron configuration, right, as we saw in the beginning of this video. More stable, lower potential energy. But what we're going to do here in this chapter, we're going to look at it in a very qualitative manner. No calculations. We're not going to attempt to quantify energy or any of this stuff. So the octet rule is going to be when we have 8 valence electrons, and the driving force is going to be something like this, an electron configuration as follow, Ns2 and P6, 8 valence electrons. Okay, that's the noble gas configuration. There are a few exceptions to that. Okay, there are a few exceptions, so let me tell you right now, then we'll come back to them afterwards. But right off the bat, we know that hydrogen, lithium, beryllium, and boron are going to attain an electron configuration like helium. Helium, 2 valence electrons. So lithium will lose 1 valence electrons, will have an electron configuration like this. Then boron should lose 3, and beryllium should lose 2 electrons. But these last two are exceptions to the exceptions. So the only one we're going to look for with 2 electrons only is going to be hydrogen and helium and lithium. 2 electrons only. But beryllium, for example, it's most commonly found having 4 valence electrons rather than 2, so it forms 2 covalent bonds. All right, so that one you need to know. Beryllium, even though it's a metal, it's going to form covalent bonds. Boron, on the other hand, instead of losing 3 electrons, what it does is it shares 3 more electrons, and it will have 6 valence electrons in its shell rather than 8, or losing 3 to be 2 like helium. When we write the Lewis structure for molecules, all the valence electrons in the atom must appear. Usually the electrons are paired, and each atom will require an octet unless it's one of the exceptions that I just told you. And the one we're going to be encountering a lot in all of our molecules is hydrogen. So hydrogen will all require 2 electrons. Then sometimes we're going to need to form multiple bonds. If those multiple bonds are to be formed, they must be between carbon, nitrogen, oxygen, sulfur, or phosphorus. I don't want you to form multiple bonds with a fluorine, for example, or a chlorine, or any of those. So those are the only 5 that I listed here for you where you form multiple bonds. And when I say multiple bonds, I'm talking about double or triple bond. So for example, a single covalent bond is when 2 atoms share a pair of electrons, only 2 electrons. So for example, a fluorine has 7 valence electrons. Okay, each fluorine has 7 valence, and it needs 8 valence electrons in its shell. So it's missing 1 electron, each of them. So what they do is they come together and they share through orbital overlapping. So now this fluorine can claim 8 electrons, and this fluorine will claim 8 electrons. That's a single bond. We represent a single bond using the Lewis model through a line like this. That line equals 2 electrons. This dash right here equals 2 electrons. All right, it equals 2 electrons. Oxygen has 6 electrons, valence electron. It needs 2. If hydrogen is available, then it would overlap with 2 hydrogen, and you end up with the following: 2 single bonds with oxygen. And now you know why oxygen is H2O, not H3O or HO. We can have double bonds. So in the absence of any other atom, oxygen can overlap with itself and share 4 electrons rather than 2. 4 electrons translate into a double bond. Or like nitrogen, for example, where 6 electrons are shared, and that's known as a triple bond. All right, so we can have single, double, or triple. The higher the bond multiplicity, the closer the atoms are to each other. All right, so a single bond is longer than a double bond, and a double bond is longer than a triple bond. This is if we're talking about length. The shorter the bond, the higher the bond energy. So if we talk about energy, then a single bond is lower in energy than a double bond, and a double bond is lower in energy than a triple bond. In other words, it takes a lot more energy to break a triple bond than it does a double bond than it does a single bond. All right, now let's see how we can use the Lewis model to draw a diagram for a molecule. I'm gonna go through the steps with you, then I'll show you an example how we apply that. All right. So those are the steps written right here. So you can always come back and read those steps, but I want to show you using an example. All right. Step 1. You take your molecule and find the sum of valence electrons of all the atoms, whether it's in a regular molecule or a polyatomic ion or whatever it is, you do that. So let's take a look at PCl3. Phosphorus has 5 valence electrons. Chlorine has 7 valence electrons, and I have 3 of them, right? So 3 times 7 is 21, plus 5 will give me 26 valence electrons. If I have an anion, let's say I have ammonium ion. Ammonium ion, nitrogen has 5 electrons. Hydrogen, it has 1 electrons, and I have 4 of them. Then this plus charge right here, for every plus charge on your polyatomic ion, you subtract an electron. So I'm going to subtract 1 for that. That's going to give me 5 plus 4, 9, minus 1, that's 8 valence electrons. All right? What if I have an anion? So if it's a cation, subtract 1 electron for each positive charge. What if I have an anion? Let's say I have a sulfate. Okay, SO4 2 minus. 6 electrons for sulfur, plus oxygen has 6 electrons, and I have 4 of them. Then I have a charge of -2, so that would be plus 2 electrons. All right. 4 times 6 is 24, plus 6 will give me 30, plus 2, that's 32 electrons. All right, that's how it works. So if you have an anion, you add 1 electron for each negative charge. That's step 1. You need to figure out how many valence electrons you have in your molecule. Step 2. You identify the least electronegative atom. Okay, in PCl3, phosphorus has lower electronegativity than chlorine, then phosphorus will be my central atom. So I'm going to place it in the center. Then connected to outer atoms with single bonds. In this case, I'm going to connect it to the 3 chlorines that I have with single bonds. All right, so phosphorus is my least electronegative. It goes in the center. Then I need to account. Each line right here represents 2 electrons. That means I used 2, 4, 6 electrons. So I'm going to keep track of the number of electrons I'm using. 26 minus 6 will leave me with 20 electrons. Step 3, you are going to place 6 dots on outer atoms. We already have 2 right there, so we need to complete the 8. So I'm going to place 6 dots on each of the outer atoms, except if it's hydrogen, we don't place anything. So I'm going to place 6 dots on these outer atoms. So I end up with 2, 4, 6, 2, 4, 6, 2, 4, 6. So when we count them, that's 18 electrons. 6, 6, and 6 times 3 is 18. I had 20 minus 18. Whatever electrons left I have, I place on the central atom. So I'm going to put the 2 dots on phosphorus, and now I got myself, I used up all the electrons. At that point, you check. Make sure that you have 8 electrons on every atom. So I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Every single atom has 8 electrons. I don't have any more electrons left. Then I'm done. My structure is done, and that is the Lewis structure for PCl3. Those electrons right there are known as bond-in pair, and the 2 electrons right on phosphorus are known as lone pairs. We're going to need those for the VSEPR model in order to predict the geometry of the molecule. All right, so these are the lone pairs or non-bonding electrons. But what if actually I don't have enough electrons for the central atom? That would be step 5. So let's take hydrocyanic acid here, HCN. We have 1 electron for hydrogen, 4 for carbon, and 5 for nitrogen. That would be a total of 10 electrons. Carbon is the least electronegative, so it's going to go in the center. Of course, hydrogen, even though it has lower electronegativity than carbon, hydrogen is never a central atom. It's always an outer atom. So that will give me, so then I place nitrogen and hydrogen, then I get 2 bonds, that's total of 4, that's 4 electrons. So I have 6 left. Then I'm going to place on hydrogen, I don't place anymore, it already has 2 electrons, so I'm going to place the 6 electrons on nitrogen, and that's what I did right here. So I used 6, now I have 0 electrons. I don't have any more electrons. But if you notice, carbon is not octet, and I ran out of electrons. Okay, carbon does not have, it has only 1 and 2 bonds, that's total 4 electrons. It's missing 4 more electrons. When you're faced with a scenario like this, then this is when you form multiple bonds. In this case, I'm going to borrow 4 electrons from nitrogen. I'm going to bring them in and form a triple bond. Now when we count, we see we have 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for nitrogen, and 2 for hydrogen, and now we got ourselves an octet. All right, everything is good and stable. That is the Lewis structure for HCN. That's why we form multiple bonds. Now let's look at an example. All right, go ahead and take that opportunity to draw the Lewis diagram for ammonia. Then I'll share with you. So pause the video, draw it, then check. Nitrogen has 5 valence electrons. Hydrogen has 1. I have 3 of them, so that'll be total 8. Hydrogen is always an outer atom, so nitrogen is going to be my central atom. By placing 2, 4, 6 electrons, I have 2 left. I place on my nitrogen, and nitrogen has 8, and that would be the Lewis structure for this. That's complete. Now let's look at another example, and that's drawing the Lewis structure for the bicarbonate ion or hydrogen carbonate ion. Now, bicarbonate ion, you can think of it as an oxyacid. Anytime you have an oxyacid, that hydrogen is always attached to oxygen. So go ahead and pause the video and try to come up with the structure. Then you come back and check the answer. Hydrogen 1 electron, carbon 4 valence electrons, oxygen 6 valence electrons, and I have 3 of them, and we have a negative charge, and that would be +1 for the charge, a total of 24 electrons. In this case, carbon has lower electronegativity than oxygen, so it's going to go in the center. Hydrogen is always an outer atom, so we write a tentative structure as such. Okay, so I draw the bonds. As I said, this is an oxyacid, so the hydrogen is attached to oxygen. So we have 2, 4, 6, 8 valence electrons are to give us the single bonds. So 24 minus 8 will give me 16. Then I'm going to place the rest of the electrons on the outer atom, excluding hydrogen. That'll be 2, 4, 6, 2, 4, 6, 2. So that'll be 6 and 6, 12, plus 4 is 16. I had 16 left, so I don't have any electrons left for carbon. Since I don't have any electrons left for carbon, I'm going to borrow from one of these 2 oxygens to form a double bond. All I need is one more bond, a double bond. So I'm going to take it from this oxygen, and I got myself a double bond. Now, hydrogen has 1 pair of electrons. All the other atoms have 4. In other words, they're octet. Then my Lewis diagram is almost done. Since this is a polyatomic ion, that means we need to enclose it in bracket and indicate the charge. All right, we enclose it in bracket, then indicate the charge. All right, now you should pause the video and work on the following practice. And once you're done, come back and look at so I'm going to give you the answers. Actually, I'll work the answers with you in the next video.